Hello everyone, this is Lakshmi Bhargavi, and my topic here today is real-time data systems, engineering for speed, scale, and resilience. So let's talk about the real-time impact too. Let's talk like 180 zettabytes of data, where the real-time demand is 30% and the latency target is less than 1 second. Expected global data volume by 2025. Modern applications demand instant responsiveness from fraud detection to personalized recommendations. Real-time data processing has become the bone of mission-critical JavaScript experiences. Where does real-time matters most? Fintech fraud within millisecond level transaction analysis, analytics, protecting billions in assets, web personalization, instant content adaptation based on user behavior and preferences, IoT sensor networks, sub-second response to critical environmental or equipmental changes. Like architecture overview, the real-time pipeline, ingesting the data into event streams, captured at a source, processing the data and transform and enrich data in flight, storage, fast query engines for instant access, delivery to the applications and end users. Event stream ingestion, getting data in fast, like Apache Kafka, distributed log for high throughput scenarios, strong ordering guarantees per partition, rich ecosystems of connectors, and AWS Kinesis, managed service with auto scaling, seamless AWS integration, lower operational overhead, and built in data retention and replay. Choosing the right ingestion layer depends on throughput requirements, operational complexity, and existing infrastructure. Both solutions handle millions of events per second when configured correctly. Stream processing, transformation and motion like Apache Flink, through stream engine with exactly one semantics. Stateful operations and event time processing for complex event patterns. Spark structured streaming, micro batch processing with unified batch or streaming API, strong SQL support, and excellent for existing Spark ecosystems. Fraud detection in milliseconds. This is a case study like number one is event capture with transaction data ingested via Kafka topics with sub-second 10 milliseconds latency. Two is real-time enrichment where join with the user profile, historical patterns, and risk scores in flight. Three is ML model scoring, where lightweight models evaluate risk within 50 milliseconds using feature vectors. Four is action and alert, where high risk transactions blocked instantly, alerts sent to security teams. Here, end to end latency like 80 to 120 milliseconds from transaction to decision. Fast query engines, the final mile. Apache Druid, optimized for time series and event data with call storage. Sub-second aggregations across billions of events. Perfect for real-time analytical dashboards. Like real-time ingestion with historical data, proximate algorithms for speed, horizontal scalability built, and ClickHouse, OLAP database designed for analytical query at scale, exceptional compression ratios and query performance, ideal for high cardinality data, vectorized query execution, native replication, and shared SQL interface for developers. Engineering for low latency, minimize network hops, optimize serialization, batch smart, not big, and cache strategically. Like when you say minimize network hops, collocate processing and storage when possible. Each network round trip adds like 1 to 5 milliseconds, designed for data locality and reduce cross center data calls. Optimize serialization. Choose efficiency formats like Avro or Protobuf over JSON. Serialization can consume 20 to 30% of processing time in high throughput systems. Batch smart, not big, small micro batches balance throughput and latency. Sweet spot is often 100,000 events or 10 to 50 milliseconds window, depending on use case. Caches strategically using memory caches for hot data and lookup tables. Redis or memcached can serve reads in microseconds, not milliseconds. Horizon beyond machine. Partition your data Distribute load across multiple nodes using consistent hashing or range partitioning. Stateless when possible, like stateless services scale effortlessly. When state is required, use external stores like Redis or distributed state management in your system processing. Auto-scaling strategies. Monitor queue depth and processing lag. Scale out when lag increases. Scale in during quiet periods to optimize costs without sacrificing performance. Consistency versus availability, the trade-off. Strong consistency, all readers see the same data immediately. Higher latency and reduced availability. Used for financial transactions and critical operations. Eventual consistency. Data propagates over time, lower latency and higher availability. Acceptable for analytics, recommendations, non-critical features. Tunable consistency, adjust per operation using quorum reads or writes. Balance requirements dynamically based on the importance of each request. There is no one size fits all answer. Choose based on the business requirements, not technical preference. Many systems use different consistency levels for different data types. Fault tolerance building for failures, like we have checkpointing, replication, retry logics, circuit breakers, where we can prevent cascading failures by failing fast monitoring downstream services and halt requests when systems are degraded. Let's talk about like front-end integration, bringing real-time web sockets and server send events, enable bidirectional or unidirectional streaming from server to browser. Perfect for live dashboards, notifications, and collaborative features. GraphQL subscriptions. Declarative real-time data into your existing GraphQL API. Clients subscribe to specific data changes and receive updates automatically. State management. Use Redux, SmobX, or just Stan to handle streaming updates in React applications. Normalize data to prevent re-renders and maintain performance. Takeaway building real-time systems. Like start with the requirements, define latency targets and consistency needs before choosing technology. Not everything needs sub-second processing. Design for failure. Assume components will fail and build resilience from day one. Monitoring and alerting are not optional. Measure everything. Instrument your pipeline with metrics at every stage. You can't optimize what you don't measure. Scale incrementally. Start simple and add complexity only when needed. Over engineering early creates technical debt. Think end to end. Latency in one component affects the entire system. Optimize the full pipeline, not individual pieces. Thank you.